18 gold hexagons, floating 1,000,000 miles from Earth, just caught light older than our solar system. Inside that light sits a galaxy that shouldn't exist yet. Now Roger Penrose, Nobel laureate, is warning something almost no physicist will say aloud. The Big Bang may not have been the beginning. I want you to picture that mirror for a moment. 18 hexagons of beryllium coated in gold, colder than anything humans have ever built, pointed away from the sun. They are not looking at space. They are looking at time. Every photon that lands there began its journey before there were rocks on Earth, before there was a solar system. When the light left its source, the universe itself was a fraction of its current age, and the space between here and there had not yet stretched to its present size. That stretching is why the light arrives red. Cosmologists call it redshift. You can call it a receipt. Each photon carries a number on its back that tells you how long it has been traveling and how far the universe has expanded while it did. That is the machine. That is how the James Webb Space Telescope works. It reads the receipts of ancient light. And for decades before Webb launched, we thought we knew what the earliest receipts would say. The story went like this. The universe begins hot and smooth. It cools. Ordinary matter falls into invisible scaffolding made of dark matter. Small clumps form first, then merge into slightly larger clumps, and much later into anything you would recognize as a galaxy. In the first few 100 million years, you should see faint, small, chaotic protogalaxies, little smudges, rough drafts, nothing organized, nothing massive, nothing that looks like it has been in business for a long time. This picture has a name. Cosmologists call it the Lambda Cold Dark Matter Model, LCDM for short, and it did not appear from nowhere. It was built to match the cosmic microwave background, the ancient radiation left over from when the universe was 380,000 years old. It was built to match the ratios of hydrogen, helium, and lithium forged in the first minutes of cosmic time. It was built to match the way galaxies cluster today. On almost every scale, it worked. For a long time, it was the closest thing modern science had to a triumphant cosmic story. Then Webb opened its eye. In early 2023, an international team led by Ivo Labbé published a result in Nature that made the field flinch. Using Webb's earliest deep field images, they identified 6 candidate galaxies sitting at redshifts of roughly 7 to 10, meaning we were seeing them as they were between 400 and 700 million years after the Big Bang. That was expected. What was not expected was their size. Each of those galaxies appeared to contain stellar masses on the order of 10 billion suns. A few pushed toward 100 billion. Objects that mature, that heavy, that finished. Sitting inside a window, LCDM had reserved for cosmic infancy. I want you to feel the weight of that. Right now, photons from those galaxies are hitting Webb's mirror. If you were standing beside the telescope in the dark of L2, the same light would be brushing your skin. It has been traveling for more than 13 billion years to reach this moment, and it insists on carrying information that our best physical model cannot fully explain. Naturally, the first response was not panic. It was suspicion. Astronomers know that photometric redshifts, the kind estimated from images alone rather than from spectra, can be badly wrong. A dusty galaxy nearby can wear the disguise of a young galaxy far away. An older population of stars can look, from images, like something it is not. Distance can be tricked. Mass can be tricked. If you overestimate how far away a galaxy is, you overestimate how bright it must be, and therefore how much stellar mass it contains. The whole Labbé sample could, in principle, be an optical illusion, so they tested it. Follow-up spectroscopy with Webb's NIR-SPEC instrument began breaking the light of these objects into fine ribbons of color, searching for the specific fingerprints that pinned down redshift exactly. Some candidates did fall. A few turned out to be closer, less massive, less impossible. That should have ended the story. It did not. Because when spectroscopy confirmed the redshifts of other early galaxies, from parallel surveys, the tension refused to disappear. Jades GS Z14-0, spectroscopically confirmed in 2024 by a team led by Stefano Carniani, sits at redshift 14. That is barely 300 million years after the beginning of everything, and it is bright, too bright, according to what the model was allowed to build in that little time. One detail refuses to fit, and that detail is not going away. Something in the first few 100 million years finished its work faster than physics said it could. So astronomers went hunting for the trick. There had to be one. Nature does not casually break a model that has survived 30 years of scrutiny. The next suspect was light itself. When you look at a distant galaxy, you do not see stars. You see a blur of combined luminosity, and you infer the number of stars from that glow. But not every glow comes from stars. A supermassive black hole feeding at the center of a young galaxy can outshine everything around it, a bright point wearing the costume of an entire stellar population. If even part of that early brightness comes from an active galactic nucleus rather than from real stars, the mass estimates collapse. What looked like 10 billion suns of stellar material might be a much smaller galaxy with a very hungry black hole at its heart. That helps. It genuinely helps. Later, Webb observations found signatures of accreting black holes in several of the most extreme early galaxies. Some of the mass came off the books, not enough of it. Then came a second correction. Star formation in the early universe may not have been steady. It may have been violent, bursty, uneven, the cosmic equivalent of a fireworks display rather than a slow furnace. If galaxies flashed into extreme brightness for short windows and then dimmed, we would preferentially catch them during their loud moments and overestimate how much they actually built. That trick, too, softens the tension. It does not erase it. And then a third possibility, stranger than the others. Perhaps the first stars were not like the stars we know. In a universe still nearly pure hydrogen and helium, without heavier elements to cool the gas, the physics of collapse changes. Stars may have formed heavier on average, more top-heavy, burning brighter for their mass. A galaxy with fewer such stars could shine like a galaxy with many normal ones. This is called a top-heavy initial mass function, and it too pulls the numbers closer to the model. 3 fixes, 3 partial rescues, and here's the quiet, uncomfortable fact underneath them. Each one works a little. None of them works completely, and you cannot apply them all at maximum strength at once without inventing an early universe that behaves very differently from the one LCDM was built to describe. Now look back at Chapter 1 with new eyes. It was never really about 6 galaxies from the Labbé paper. It was never about one bright object at redshift 14. Independent surveys, SEERS, JADES, Cosmos Webb, kept pulling more of these things out of the deep sky. The problem was never a single misread photograph. The problem was the whole early population. Wherever Webb pointed, the young universe looked older than it had any right to look. In 2023, the cosmologist Michael Boylan-Kolchin framed it precisely. He treated the Webb galaxies as a stress test. How much of the available cosmic material could actually be converted into stars that early, and how quickly before the standard model would have to break? His answer was uncomfortable. The efficiency required was high enough to sit at, or beyond, the edge of what LCDM comfortably allows. Not proof of collapse, something worse. A warning sign inside a model that had never needed warning signs before. This is the moment where a name almost no cosmologist wants to invoke walks into the room. Roger Penrose, Nobel laureate, the man who proved, with Stephen Hawking, that general relativity forces singularities inside black holes. And Penrose has been saying, quietly and stubbornly for years, that the Big Bang may not be what we think it is. His proposal is called conformal cyclic cosmology. The idea, stripped of its equations, is this: our universe expands forever, its matter decays, its black holes evaporate. Eventually there is nothing left with a mass, nothing to define a scale, nothing to distinguish very large from very small. And in that state, Penrose argues, the endless cold future of one universe becomes mathematically indistinguishable from the hot, dense beginning of another. Aeon after aeon, each Big Bang is the last exhale of the previous one. Penrose and Vahe Gurzadyan went further. In papers from 2010 onward, they claim to see faint concentric rings and warm spots in the cosmic microwave background that they called Hawking points, alleged fingerprints of black holes from a previous cosmic aeon whose evaporating light was branded onto ours. The Planck team and independent groups pushed back hard. The statistical significance is disputed. The mainstream does not accept it. But now, sit with the possibility. If the early universe carried in structure that was not born inside it, if the smoothness of our Big Bang was not perfectly smooth, then the galaxies Webb keeps finding, mature too soon, luminous too early, organized before they should be, might not be young at all in the deepest sense. They might be the visible edge of something that survived the crossing. The question is no longer whether one telescope image can be explained. The question is whether the beginning of everything is a wall or a door. Now separate the layers carefully, because this is where the story either becomes honest or becomes noise. At the highest level of certainty sit the observations themselves. Webb saw those galaxies. NIR spec confirmed the redshifts of several. The photons are real. The colors are real. The instrument works. Nothing about that is in serious doubt. One step down, sit the calculations. Stellar masses derived from that light. Star formation rates inferred from those masses. Ages estimated from spectra. These are careful numbers, but they depend on assumptions about dust, about how stars distribute themselves by mass, about how much of the light comes from stars, and how much from feeding black holes. They can move. They have moved. And in almost every reanalysis, they have moved in the direction of easing the tension without erasing it. Below that sits the interpretation, the claim that LCDM is under real stress. Boylan-Kolchin's stress test lives here. It is not a proof of new physics. It is a boundary marker. It says that if these galaxies are as massive as they appear, the standard model must either bend or invent a very efficient early universe. And below all of that, in the deepest, most speculative basement, sits conformal cyclic cosmology and the Hawking points. Beautiful ideas, mathematically serious ideas, but at present contested by careful analyses of the same CMB data Penrose relies on, and not embraced by the cosmological community. Now, honestly, what is the most likely resolution? Not portals, not previous universes. The most likely story is that early galaxy formation was significantly more efficient than anyone expected, that the first generation of stars was heavier and brighter per unit mass than the ones we see today, that black holes seeded themselves fast and contributed to the glow, that bursty star formation and updated dust models will keep chipping away at the discrepancy. In 2 or 3 years, most of the tension may be gone, quietly absorbed by better astrophysics, and still, something will remain. Because even the conservative fixes push cosmic dawn earlier than we thought. Even the ordinary solutions require an early universe that assembled itself faster than the previous generation of models predicted. The clock of creation is being reset in small, undramatic steps, and each step makes Penrose's warning a little harder to dismiss out of hand. Not because he has been proven right, he has not, but because the direction of the arrow points toward a beginning that had more going on inside it than we had ever admitted. Come back to the mirror. 18 hexagons of gold hanging in the cold beyond the moon's orbit. Yesterday, you would have called it a telescope, a very expensive camera pointed at things far away, but a telescope collecting light. This old is not really pointed outward, it is pointed backward. And if any of the wilder possibilities are correct, even fractionally, it is not just pointed at our universe. It is pointed at the thin membrane between our universe and whatever came before. That mirror is a memory surface. It records what light remembers. And now come closer, all the way in. Look at your hand. Every carbon atom in it was forged inside a star. Every iron atom in your blood came from a stellar death. The chain of ancestry that runs from those atoms back through supernovae, back through the first stars, back through the collapse of primordial gas, ends at the very moment Webb is now imaging. If those early galaxies formed impossibly fast, then your body is younger than expected in one sense, and older than expected in another. The material that built you was cooked earlier than the model allowed. You are made of evidence. So what is the honest answer to the title? Did Penrose prove the Big Bang never ended? No. Did Webb confirm conformal cyclic cosmology? No. Did the James Webb Space Telescope find something strange? Yes. It found a young universe that, in image after image, refuses to look as young as our best theory said it should. And Roger Penrose, watching from the edge of orthodoxy, is naming the possibility that most physicists will not name in public, that the moment we call the beginning may be a crossing, not an origin, that the smoothness we treat as a start may carry echoes of an older cold. The evidence does not prove him right. The evidence does not prove him wrong either. And in cosmology, that middle space is where real revolutions germinate. Hold the mirror in your mind one last time. 18 gold hexagons, cold and still, gathering a signal that traveled across almost the entire history of matter to reach a moment inside your attention. Somewhere inside that faint arriving glow are answers we already have, answers we will get in the next decade, and answers that may still be sleeping. If cosmic structure existed before it should have, then the question that remains is the one no telescope has yet been built to answer. What exactly was the Big Bang the beginning of?